Welcome to lecture 6. Now here for the first time we're going to be looking at motion in more than one dimension. We talked a little bit about what that means early on. The short answer is essentially it means that we need more than one number to accurately describe the position of an object. Like, things don't all happen along a long straight line anymore. Things can move up and down or left and right, or they can move north and south, east and west. Of course, we can also extend this to 3 dimensions: north, south, south, west, east, up and down. We could mathematically extend it to 4 and 5 and 10 and 100 dimensions. There's nothing that stops us from doing that, but it becomes physically less meaningful, at least at the level that we're doing this course at. Okay, so in this lecture we're just going to go through an extended example just to get a feel for how to think about motion in more than one dimension. And then in the next lecture I'm quickly going to review the notion of vectors, because they're crucial. We're going to be using them here already, but we're going to look at them a bit more systematically in the next lecture. And then we'll move on to motion in 2D with accelerations and more problem solving, turning motion, circular motion, and there'll be lots of fun examples, of course, we'll do in the process. Alright, so we'll be looking at boats trying to cross a river. They want to end up in the right place. And so the concepts we'll meet are velocities and displacements in 2D, so we are not going to worry about acceleration right now. We'll come to that very soon. And the tools that will have to form part of your toolbox, part of your repertoire, is we're going to need trigonometry. We get this idea of vectors and taking components of vectors, how to deal with those. And so conceptually, one fundamental notion that underlies all of this is the independence of motion in different directions. So what I mean by that is that if you're trying to figure out, well, how quickly are you moving left-right? If you know the velocities, accelerations, and so on in the left-right direction, then it does not matter what happens in the up-down or north-south or whatever direction. That is irrelevant. Assuming you have the information that you could solve a 1D problem left-right, well then it does not matter what happens in the other direction. We'll see that in action. We'll see what that means. It is in a way almost more like obvious than it sounds. It sounds very abstract, it sounds very strange, but it's hard to think of it being any other way in a sense. Okay, let's get started. So here's our example, our first case for example. A river flows straight south at 2 meters per second. We've drawn it here. Let's indicate this. This is meant to be the river in the middle of the page. So the river is gonna always just go south. I'm just gonna draw it like this at 2 meters per second. And then there's some trees here, some mountains here, a little dock here. It's not the point. So the river goes 2 meters per second south. If a boat that can go 5 meters per second in still water were out on the river, how might it move? Okay, so maybe we want to give this thing a name, these 5 meters per second. We might call this the engine speed. I don't have a better name for it. Let me just label this. This is not some kind of official term. I'm going to call it. Right, so what does this mean? It means that if you put that particular boat out on a lake, perfectly still, it'll go, turn on the engine, it'll go 5 meters per second. Now in the river, of course, the situation is different, because the water as a whole is flowing south. So how might that move? Well, if the boat, let's draw a boat in different places. Let's say my boat is right here. If the boat decided to head straight south, I'm going to draw it a bit like a space rocket. You can please see where the front of the boat is, right? The front's pointing south right now. Then, well, it's gonna go 5 meters per second on the water, but then the water underneath it is gonna go down 2 meters per second, and so its overall motion is gonna be the combined 5 meters per second. But then the river takes it down 2 meters per second more. So 2 meters every second. And so in total it's going to travel downstream by what? By 7 meters every second. Right, so the combined overall motion is this. In this case, you can actually just easily calculate it. 7 meters per second. So make sure that makes sense to you. It's a little bit like running on an escalator. Right, the escalator moves beneath you, but you're also running on it, so overall you might be able to run faster if you run the same direction as the escalator, because you can still run at the same speed as before relative to the ground beneath you. Same idea here. Okay, let's suppose the boat want to go a different direction. Let's say the boat they wanted to go up. Well, in that case, it might go up relative to the water at 5 meters per second. So if somebody drops something in the water next to it, well, after 1 second, the boat will be 5 meters away from that that rubber duck perhaps that has been dropped. But of course, in the same time, the river is going to take us back down 2 meters per second. And so to someone on the shore who's watching this whole thing happen, the boat would only be moving up 3 meters per second. Okay, so this is my overall motion. Might say my actual motion. Right, in red. So those two cases I think are fairly straightforward. Right, you're going with the river, you're going against the river, and in this case the river is helping you. In this case the river is sort of fighting against you. And I hope it is obvious how to add those velocities. Now, what if the boat were going some other direction? Maybe the boat is going straight to the right. That's actually the case we're going to be looking at in more detail in just a minute. So in that case, the boat will be going 5 meters per second to the right. But the river is going to take it downstream 2 meters per second. In fact, it's going to take it down, the whole river. So if you drop a little rubber duck at the back of the boat, well, after 1 second, the boat will be 5 meters away from it. It will have moved, 5 meters to the right because it's going 5 meters per second. But both the rubber duck and the boat would have drifted down by 2 meters per second. So relative to the water, you're still moving 5 meters per second. But overall, you're going right and also drifting down. How do I figure out the overall motion? Well, let's just ask, where am I after 1 second? We'll have moved 5 meters over. We'll have moved 2 meters down every second. And so overall, it looks as if the boat was going like this. Well, it is going like this. Here we'll have to think more carefully about what the speed of the boat is. So it's going in this direction. What distance has it traveled from here to here in 1 second? Well, it's going to be by Pythagoras, right? This right angled triangle. 5 squared plus 2 squared is 29. So that would be the square root of 29. That many meters per second. 5.4 thereabouts. Okay, you just write down the Pythagorean theorem. Now, of course, the boat might also be going at some other direction, right? It might be going maybe like this, some funny angle. In this case, well, if it be going, I'm not going to do the math right here, going 5 meters per second this way if the river wasn't moving, but the river is moving, so the whole thing is drifting downwards. So after 1 second, I have to add the downwards drift. And so the overall motion will actually look like this. So not straight necessarily, slightly upwards in this case. Or I could imagine that maybe the boat is aiming downwards, like downriver, like this. In which case, well, I'm going 5 meters per second down, but then like diagonally down. But then the river is gonna add to that motion another 2 meters per second straight down. And so if I track the tip of the boat again, the actual motion is going to be in this direction here. Now it seems obvious when we add displacements, like the boat's going from here to here and from here to here. Of course, realistically, it's not going in steps, right? It's going to go along this direction here, because you could play this game with, well, after 0.1 seconds, it'll be 0.5 meters over and 0.2 meters down, and so on, right? So it's a continuous, but to establish what is the direction of the velocity, I can add the individual velocity vectors, as they're called. You know, the vectors have a direction, a magnitude. You can add those, and then by just putting the arrows sort of tip to tail. It's kind of the buzz phrase when adding vectors. Tip to tail. And the result depends not only on how long they have the same length, the green one, the blue one, the same length in each case, but it depends on the relative angle between them, the relative direction between them. They're hugely different answers. And what we can say, though, is that the maximum speed we're going to get is 7, the minimum is 3, because in this case they just add, in this case they just subtract, and everything else is somewhere in between. So, adding velocities together, different contributions to the velocity, in this case the engine and the flow of the river. Well, I just look at the individual velocity each one provides and can think of it as a displacement in 1 second from here to here. Well, then I'm going to add a displacement from here to here and I get the overall displacement. So make sure that makes sense to you before we move on. Okay. So, here's our same example, but now we're told the river is 150 meters wide. The boat's now heading straight east. How far will it drift downstream when crossing the river? So straight east was this case here, right, where this is at right angles because our river is going straight south. So let's say I'm just going to track a point. The point is the tip of my boat. We're going to start over here. Now that it's heading straight east, a bit of terminology here. We are heading, right? It's kind of pointing straight east. It means it's trying to go straight east. Never mind what the river does. And it does so at 5 meters per second. And then the river is going to take us down by 2 meters per second. So we've already worked out what the overall speed is root 29, but actually we don't really care so much here. Right, this is my overall velocity. So the question is, how far do we drift down by crossing the river if we're heading straight east? The boat is pointing straight east. Well, if there wasn't a flowing river, the boat would just be doing this. And we're there, we haven't drifted. But of course there is the flow of the river, and so we do drift. Now lucky for us, we actually know the direction that we're going in. Let's see if I have a ruler somewhere to make this a bit more accurate. Yeah, let's do it like this. There. So we know we're going in this direction, right? That our velocity vector points. So I can just solve this whole thing geometrically. We're going this way. This is if you are hovering above the helicopter, this is the actual path you see, right? Now, where is that? Well, the way we can solve this is just by looking at triangles. Because the little triangle here and the big triangle, right? So little triangle is a triangle of velocity vectors. Big triangle is going to be the overall displacement from one side to the other. Displacement from here to here, but the contribution of the engine motion is from here to here. The drift is from here to here. Well, those two triangles they are similar. I hope you remember what it means. Essentially means that the sides have the same ratios, and that's guaranteed if they share at least two angles. They do. They both have this angle here because it's part of the triangle, and this is a right angle, this is a right angle. So actually this is also the same as this angle. And crucially, the ratio of their sides is similar. So what does that mean? It means this relates to this with the same ratio as this relates to this. Right, so use similar triangles. Every time we discuss a math concept that you maybe vaguely remember, you don't quite remember, if you're not sure, look it up, remind yourself, because we need all those tools. So don't say, oh yeah, similar triangles, don't remember what they are, but let's get going anyway. No, pause the video, look up what they are, in your notes, online, in your textbook, whatever, doesn't matter, but you need to be on top of those little mathematical tools. Okay, so let us then work this out. Similar triangles means sides have the same ratio. So 5 meters per second over 2 meters per second. What's this? This is the ratio of this length to this length. Of course, those lengths represent velocities. Right? This over this is the same as this over this is equal to the width, W, 150. That's the length from here to here, divided by, let's call it this distance, right? This is the corresponding side of the big triangle, that is corresponding with this one. So let's call this distance D for drift. You can always label, when you have a nice diagram, you can always just label different distances and quantities, so then it's unambiguous what you mean. Right? If I just write D without showing you, you're like, what is D? I don't know. Well, I've labeled it, right? So you know what I mean by D. So we can solve this, and we're going to get that D must be equal to 150 meters times 2 over 5, which is 60 meters. Right, so we're drifting downstream by 60 meters. There's a different way we could have solved this. That is by looking at the motion. We might say the following, okay, how long is it going to take the boat to get to the other side? Never mind where I'm going to hit the other side, but how long is it going to take the boat to reach the other side? And then how far have I drifted in that time? Well, let's work it out this way. So time to other side well, time is distance or displacement divided by the velocity. Should be familiar. Right? Velocity is displacement over time, so just rearrange this. Now in this case, I only care about the west to east displacement. So I'm gonna say this is 150 meters divided by the velocity, write it like this, west, east. I haven't defined it, but by labeling it this way, this is unambiguous. We say this is the west-east component of the overall velocity, which also happens to be the component due to the engine, right? Because the river just takes us south, the river does not contribute to any motion left or right. So the 2 meters per second are totally relevant for getting across the river, because only this part here is right now what's taking us across. So this is going to be 5. It's 150 meters divided by 5 meters per second, which comes to 30 seconds. And so we drift by, when we write down our D is equal to the velocity in the north-south direction times the 30 seconds, because that's the time we spent on the water. We figure that out from the motion across. Well, this is going to be 2 because it's only the river in this case that's taking us north to south. The engine of the boat has nothing to do with the north-south motion, right? It only takes us sideways. So 2 times 30 makes 60 meters. Okay, that's reassuring. We get the same answer that we had up there. So here we've seen this independence of the different directions, right? To figure out how long does it take to get across, we were able to completely ignore the vertical motion. We knew the displacement in the west-east direction, and we knew the velocity in the west-east direction. Everything else didn't matter to figuring out something about the west-east motion. In our case, that was the time from this side to this side. And that then allowed us to figure out something about the north-south motion, because we knew how long we were spending on the river, and we knew then how quickly we were drifting down. So suppose now we do actually want to end up on the other side. What can we do? This is the last part. The boat does not want to drift. Which way should it head, and how long will it take to cross the river? Okay, so here's where we're going to start. Now, your intuition might be the following. Intuition might be, well, okay, if we don't want to drift down, maybe we just take this same angle and sort of aim upwards like this. It's actually going to give you the wrong answer. And hopefully you'll be able to see why that idea does not work. Let's think about it. So we want to move across, so we want to move, right, in this direction here. We want this to be our overall motion. Right, I want my boat to end up moving like this. So I'm going to draw my arrow that represents the overall motion first. I've been using red, remember, for the actual motion of the boat. As you're looking at it from above, you know, it should be moving this way. Now hopefully it makes sense to you that therefore, because the river is going to try to take us down, we have to sort of angle up. Right? So I know the river is going to take me down south, so I sort of know it's going to do this. So I know that I need to find the right angle to make it happen like this. Right. But this is what my engine does. And this is what the river does. But because I very smartly picked the right angle here, it's not the right angle, right, but the correct angle here, that means the two conspire to create an overall motion that takes me across. So the reason then that this isn't just, it looks sort of similar as if I just flipped it up, but actually those triangles here, this one here and this one here, they're different, because in this case the 5 meters per second is the horizontal one. In this case the 5 meters per second is going to be the hypotenuse of the triangle. Alright, so this, whereas this hypotenuse here was the square root of 29, or about 5.4. So it's not just flipped up. Looks similar, but not quite the same. I've written down what I know. I know my engine puts out 5 meters per second in some direction like this. The river takes me down 2 meters per second. Now ideally I should have drawn this exactly, you know, so 5 units long, this 2 units long. I eyeballed it here, but that is fine. I know it's just a sketch. I'm not actually going to measure the angle. Okay, so we want to find this angle that will tell us the direction. Let's give this angle a name. We like to use Greek letters for some bizarre reason. Let's call it alpha. And so I can just use trigonometry, right? This is a right angled triangle. Here's the right angle, because I know I want to move straight east, but the river goes straight south. And so those are right angles to each other. And so what am I getting? I'm going to get that well, this is the opposite of this one, the opposite of the angle, excuse me. So it's going to be sine of alpha equals 2/5, 2 over 5. Right, opposite over hypotenuse. And so alpha is going to be equal to 23.58 degrees. I think. take the inverse sine of 2/5 and make sure you express it in degrees if you want in degrees. If you want to express it in radians, that is even better. Express it in radians, but make sure you know which one you're expressing it in. Like you know which mode your calculator is in, or whatever tool you're using. Your trigonometry table, if you're a bit old-fashioned. Right, so this angle here is 23.58 degrees from trigonometry. Okay, so that's my direction. I'm gonna head 23.58 degrees. I can call this angle north of east, right? So to be unambiguous, I might write it like this, because east is this way, and I'm turning north from east by what angle? By 23.58. So how long is it going to take us across? Well, 5 meters per second, 150 meters, 30 seconds, right? No, because only part of the motion of the engine actually takes us across, right? Part of that contribution to the motion is to take us upstream. So you want to figure out what is the length of this. Well, the length of this, right? The length, of course, represents a velocity, right? All lengths here represent velocities, but we can still do geometry just the same. So this, because this is the hypotenuse here, I've got that 2 squared plus, what should we call this? Let's call it VE, because the velocity east, plus VE squared equals 5 squared. And so I get that VE, 25 fourths, this must be 21. VE is going to be the square root of 21. What does that come to? Let me think. Something around 4.6 meters per second. Right. So the actual motion sideways is 4.6 meters per second, and accordingly it's going to take a little bit longer to get to the other side, right? Because we had to use part of the motion of the engine to go upstream, to counteract the downstream motion of the river. So overall motion is sideways. Let's find the time. Well, the time across is the width of the river divided by the velocity east, right? That's 150 meters divided by 4.6 meters per second. What does that make? I think that's something like 32.6 seconds. So slightly longer. Surprisingly, it's only about 2.6 seconds longer. So actually, doing this, you might think, oh no, 2 meters per second are needed to stop me from drifting. But actually, you're still almost going the same speed. You're going 4.6 rather than 5, and you're only taking 2.6 seconds longer. And this illustrates that, look, you don't just like say, it's not like 2 meters per second go up, so there's 3 meters per second left. No, that's not how vectors work, right? You really have to look at the geometry and consider directions, work with the angles, trigonometry, Pythagoras to figure it out. And you'll get lots of practice doing it, but if you're a bit shaky on those concepts, why is it sine, not cosine? What's tan anyway? Make sure you review that right now, because we are going to need it. Okay, so we're going to look at components, taking components of vectors and so on in a little bit more detail in the next lecture, and I will see you there.